All right, welcome to topic 8.9 in the AP Calculus curriculum, volume of disk method revolving around the x or y axis. Today we're going to calculate volumes of solids of revolution using definite integrals. Volumes of solids of revolution around the x or y axis can be found using definite integrals with what we call the disk method. You'll see what's called disk method here in a few moments. We're going to start. This first video is going to cover these three parts of our lesson. We're going to explain how revolving a curve around an x-axis generates a solid. And we're going to create a cross section by revolving one infinitesimally small rectangle at a time. And then we're going to integrate the volume of one of those cross sections, the expression for one of those cross sections, to get the volume of the entire solid. And so that's how we're going to do this. When we start talking about revolving a curve around an x-axis to generate a solid, I want you to look at a curve we have set up here. And Desmos, I have graphed this function, and what I mainly want you to pay attention to is this part of the curve. So we're going to copy that and bring it over here on our notepad. And I want you to look at this picture, and I want you to envision, just if we took this right side, which this intersects at 1 and this intersects at 2. So we took this right side, and if we revolved it around the x-axis, then what you would see, around the y-axis, what you would see is this would form a bell, where this would form a solid bell if we were to revolve that around the x-axis, around the y-axis, I'm sorry. And so when we talk about doing this, let's go ahead and start draw. Sorry, still you're trying to figure out how to use this thing. When we talk about doing this, what we're doing is we're taking one rectangle. So if we were looking at a cross section, whoops, that's not what I want to do. If we're looking at a cross section and revolving around the y-axis, we would take one rectangle whose width would be dy, and if we were to revolve that, we could take that one disk, this would be a disk, whoops, and if we took that one disk out, we could work with it like we did our cross sections in our other things. And if you notice, when this disk is laying on its side like this, we're looking at a cylinder, and the height of that cylinder is dy. The radius of that cylinder is the x value so we would have to solve our equation for y or for x, which wouldn't be easy on this one. But if we did that, if we solved it for x and then we did all the things we did before to revolve around the y-axis, we could make this work. But right now, this would be our x value, the radius would, and we could get the area of the base of this, whoops, so we could end up with a volume of one of these cross sections, all right? And the volume of one of these cross sections would be pi times the radius squared times dy. Now, if we were revolving this around the x-axis, we'll create a different kind of solid. We would integrate, or we would be revolving this entire area bound in the first and second quadrants. If we were going to do that, we would take one rectangle, and you can see that if we revolve that around the x-axis, that it would create a disk also. And if we took that disc out and we laid it on its side, we would have another cylinder where the height this time would be dx. And this time the radius would be the curve, f of x. And so we could find the volume of this one cross section that we pull out, and that would be pi times the radius squared times dx, which in this case would be pi times f of x squared times dx. That would be the volume of one of these cross sections. And since doing that, let's see, if we were going to integrate that, this is one we could integrate. Let's go ahead and draw that cross section again. Where the radius was f of x, the width was dx, and so the volume of one of those cross sections was pi times f of x squared times dx. That's the volume of that cylinder, that cylindrical disc that we're talking about here. Here, if we were going to do this, we would integrate from, if we wanted to get this whole thing that would look, let's look at what it would look like. Oops. Well, not a very good drawing. Let's try this again. It'd be easier if my pen was working. This would be a really kind of weird looking solid, but if we revolved it around the x-axis, we would take this cross section and we would take cross sections everywhere along here, infinitesimally small. Remember, we're taking the limits as they go to 0. It's a little big, but you get the picture. We're making all those cross sections to form a solid. So we're going to integrate one of these from the boundaries, -1 to 1. Bring the pi outside because it's a constant. We would be integrating f of x squared dx from -1 to 1. And that's how we're going to end up generating these solids, getting the volume of these solids. This is going to be the volume of the entire solid when we do the center of this definite integral. That's how we're going to end up getting the volume of these solids that are created by rotating a curve around the x or the y axis.